In this next series of videos, we're going to take a look at simple harmonic motion. And simple harmonic motion is something that we see a lot of in our everyday lives. If you study the motion of somebody that's in a rocking chair, that could be considered a harmonic motion. If you look at the tines of a tuning fork or the strings of a guitar, they vibrate back and forth, and that motion is generally considered to be simple harmonic motion, all the way down to the vibration of atoms. So the characteristic of simple harmonic motion is going to be that we see vibrations and or a repeating kind of motion. But what specifically makes motion simple harmonic is that it's going to be created by a linear restoring force. So simple harmonic motion is a repeating motion. Oftentimes we just see it as a vibration, or we refer to it as an oscillation. But the key feature to simple harmonic motion, what really defines the motion as simple harmonic motion, is that it is caused by a linear restoring force. Now, a linear restoring force is not one which is constant. A linear restoring force is one which increases at a linear rate as the object moves further and further. So the easiest example that you can relate to is just going to be an ideal spring, a spring which obeys Hooke's law. And so, in fact, we're going to be using springs to help come up with some of our models to help us understand the behavior of simple harmonic motion. If you refer to the system, it is sometimes called a simple harmonic oscillator. Okay, so the system is a simple harmonic oscillator. And examples of that would be, for example, a mass block system. So you put a block on a frictionless surface, attach it to a spring which is attached to a wall, and that block is going to oscillate from side to side. It's going to go left and right. And so that would be a simple harmonic oscillator, but the block itself is in simple harmonic motion. Another example would be an earth mass system, and that you would recognize as a pendulum, and the pendulum is going to swing to and fro. All right, so those are examples of simple harmonic oscillators. So like I was saying before, we will use coil springs to help us develop the fundamental ideas behind simple harmonic motion. And we're also actually going to be using a spinning disc to do the same thing as well. Okay, so first let's review a few terms that are going to be central to understanding simple harmonic motion. And the first is going to be equilibrium position. Okay, and the equilibrium position, if you recall when we looked at springs, the equilibrium position is just where the spring was at its natural length. Okay, the equilibrium position is also noted by the fact that there is no net force at the equilibrium position. Another term that we need to review is the restoring force. And restoring simply means that it points toward the equilibrium position. And the last really big idea that you need to understand for doing simple harmonic motion is that the force is not constant. All right, and that is a really, really big deal. Okay, because what's going to happen is when it comes to our equations of motion, you're going to want to use equations like d equals v initial t plus 1/2 at squared. Even though we come up with totally different equations, in your desperation for completing a problem that you don't fully understand, you're going to go back to what you already know. And so, but these equations, all of these equations here that we learned back in kinematics earlier, they're not going to apply because of this. The acceleration was constant acceleration. So it wasn't changing in time because the force was constant. So for example, if you drop something, it's going to fall with a constant acceleration of 9.8 meters per second squared. And the reason it's falling with a constant acceleration is because the force of gravity is constant. It's not getting bigger or smaller as the object falls. And so because the force is not constant, we have to come up with a completely different way of analyzing the motion of the object that cannot utilize the equations that we had before. Okay, so let's take a look at some other basic properties associated with simple harmonic motion. And what I have here is a block which is attached to a spring, and it's on a frictionless surface. Alright, so here's a coiled spring. The spring is actually compressed, and at this location we have the equilibrium position. At this location we have one extreme of the motion, and at this location we have the other extreme of the motion. And these two extremes of motion we're going to refer to as the amplitude. So it's just the maximum displacement from the equilibrium position. So this will be minus the amplitude, and this will be plus the amplitude. All right, now at this position, the force is going to be at a maximum, and that's because the spring has been compressed as much as it's ever going to be compressed. And since the spring obeys Hooke's law, which is F equals minus kx, the bigger x is, or the bigger the displacement from the equilibrium position is, the bigger the force is going to be. Now, what does that tell us about the acceleration? It tells us that the acceleration is also at a maximum, and that's because of Newton's second law. The acceleration is equal to F net over m. And finally, the other characteristic we're interested in is the velocity. And at this location, the velocity is going to be 0 because it's a turning point. So it seems almost counterintuitive that the maximum acceleration occurs when the velocity is at a minimum. But that is the way it is. Okay, so let's take a look at it sometime later. And we have here, let's see here, here's minus the amplitude, here's the equilibrium position, and here's plus the amplitude. Minus A, EP, plus A. And let's see here, we have our block. It's now going to be located in this position. And our spring is now at its natural relaxed length. Okay, so at this point in space, what do we know about the force? The force is equal to 0. And if the force is equal to 0, what does that imply about the acceleration? It is 0. And then finally, the velocity is going to be at a maximum. Now, why is that? Because in this location, the force is at a maximum. It's pushing to the right, so the acceleration is to the right. And if there's an acceleration, that means the speed is changing. So the most rapid change of speed occurs in the beginning of the motion, and by the time it reaches the equilibrium position, the force here is equal to 0, And so A is equal to 0. There can be no delta V. There can be no change in velocity. So at this location, the velocity is at a maximum. And then finally, we have the block being all the way out here at the positive amplitude. There's the equilibrium position and minus the amplitude. Okay, so the block is located right here. And our spring is now stretched out as much as it was compressed. And at this location, what do we know about the force? Well, the force is going to be at a maximum. The acceleration will be at a maximum. It looks exactly like being at the minus amplitude. And the velocity is equal to 0 because once again we are at a turning point. So when we look at simple harmonic motion, one of the big ideas is that the system is in a continuous state of transition. It's going to go from 0 acceleration to maximum acceleration, or 0 force to maximum force, or 0 momentum to maximum momentum, or 0 kinetic energy to maximum kinetic energy. So you see, I've used all 4 perspectives to describe what's happening with an object that's in simple harmonic motion. So don't ever let anyone tell you that you can't use all 4 of those perspectives in trying to understand a physical situation. It just means that not all 4 perspectives are always very helpful in understanding what's going on. And we're going to see that here in simple harmonic motion. The one perspective that really doesn't get much attention is impulse and momentum. But nonetheless. Okay, so that is the basics behind the motion. Now, we have one term that we need to revisit, and that is something called the period. And the period, we use the letter capital T. And the last time we saw period was whenever we were studying circular motion. And the period is a constant within a problem. And this is why you were never permitted, or you should never write the variable for time, little t, as a capital T, because we do designate capital T as the period, which is a constant. So make sure that you're using little t for time and capital T to represent the period. Period, it's measured in seconds. That's the SI unit. And it is the time to complete one cycle. All right, now one cycle is from one position all the way out and then all the way back. So it's going to go from minus the amplitude to plus the amplitude all the way back to minus amplitude. And that's going to be one complete period. What I've diagrammed up above happens to be only half of a period. So here, t is equal to 0 periods. Okay, 0 capital T. Here we have t is equal to 1/4 the period. Here we have t is equal to 1/2 the period. And if we continue this on and on our way back, then we would have 3/4 of a period, and then finally 1 full period by the time we reach the negative amplitude once again. Okay, the other important term, which is very closely related to period, is called the frequency. And the frequency is denoted with an italicized F, and the frequency is 1 over the period. So it's the number of cycles in 1 second. The units for period, the units for frequency are going to be the reciprocal second, s to the minus 1, or we could write it as 1 over s, Or the more common term is hertz, but the hertz is just the 1/2. All right, and our relationship between frequency and period is we have frequency is equal to 1 over the period. Frequency equals 1/t. Now, in the next video, we're going to take a look at our first perspective, which is the kinematics perspective.